Hi everyone, so I'm Desire. Today we've got one of our students, Venkat, who has just completed the course ROS Basics in C++, and today you'll be doing a presentation on a real robot to see to show us what he has done. So over to you, Venkat.
Hello, can you hear me well?
Yes, I can hear you.
Can you see my screen as well?
Yes, I can see your screen.
All right, thank you. Hello, my name is Venkat. I have done some coursework related to ROS2, and I would like to present a small project that actually happened to come together. I'll be presenting a series two items here. One is basics and the URDF, which is robot definition format. First, we'll start with basics. For the project is something like this. First, I would like to you to focus on this area. Uh, let's assume that the red dot is a robot, right? The project revolves around making sure that we can move the robot along this line and move it back. After one lock, we actually stop it. There are multiple components that are at play here. We'll go one by one, go into the details. First is that we need to detect the nearest wall, which we do. Then we move forward, and at a safe distance from the wall, we need to turn. Okay.
Sorry,
And
Venkat. Can you just make the screen with the slides a little bit bigger? So,
uh,
or you can make it full screen so that we can see what you're talking about.
is this any better? Is this any better?
It's too small. You can maybe move the one with your picture to the side.
How about that?
All right. It looks clear. I don't know if you can maybe share one window, the one that you are presenting on.
Oh no. If I do that, I need to reshare again for the. I can do that if you want me to do that. But this is good. We can see it right now. So I can talk through it.
All right.
So this is so you can see you can see this picture, right? Correct. You see it well.
Mm-hmm.
Okay. Okay, so we need to move the robot in this direction, and then we need to detect that at a safe distance we actually turn a left, and then turn around, and then calculate that there is one lap, and then we need to stop. So this is the objective. There are multiple items that actually go into some of this. Like we need to detect the nearest wall. We need to move towards it because we need to, at the safer distance, we need to move towards the wall first. Align with the wall. So we need to do a 270 degrees rotation so that our movement aligns with along with the wall. Then we need to send the movement commands for the robot to move, which is setting the linear velocity and angular velocity related parameters. Next up, we need to interact with we need to record odometry. We'll talk about action server. We need to receive the position data later. And then we need to publish velocity commands to make sure that we actually set the amount of velocity that it needs to take. We need to take the distance related record parameters from the odometer. And we will talk more about the implementation of the action server detecting of the lap distance. So these are the small parts. Now we will actually first try to see a demo and then talk about what it actually looks like.
All right.
Okay, let me try to talk to the real robot. Is that good? Is that okay? I'll first show a demo,
Yeah.
and then we will talk about the.
Go for it. Go for it.
I am connecting to the robot right now. Okay, there we are connected. So this is the workspace that I was working with. It contains multiple projects. Sorry, I was working around this. We will focus on this particular amount of source code in one specific areas. First, I'll pick up the commands I have said to make sure this is a quick process. So here's the robot. Should come up anytime now. It usually takes 2 times and then it works. you know. Okay, there it is. So the robot is at a different place. So what I'm going to do is that I will try to bring it back so that the distance calculation for the lap is correct. So this is the twist keyboard. I will use this keyboard to bring it to a place closer a little bit. Okay, so forward. Okay. All right, there you go. Hits. All right. Now I will try to start the robot. So first I will start an action server. The action server records the odometry settings. We will shortly see what it looks like. And then I will start the main program. Okay, so please let me start it. So that starts the server. It is recording a distance. Right now the robot is not moving, which is fine. It keeps recording 0. So they're not sick. Okay. So here we are starting the main file. So when we start the main file, the robot is going to start using the leader data to actually keep rotating. It will try to find, it will do 3 actions. I will walk you through that. What are the 3 actions it will actually take? So if you can see it. So it actually takes a turnaround.
Okay.
It starts movement. Yes, there you go. So it starts moving along the edge. It is needs to. So we keep recording the data on this
Okay.
side. So it will notice that there is an obstacle coming and it will take a left. It will take 1 lap and then it will turn around. Usually this takes exactly 40 seconds or so. So So as you can see, the distance is reducing and it has finished the lap. We started over here. It finished the lap, it stopped it.
Yes.
And it has printed the coordinates of X and Y coordinates that it has taken along with the theta parameter. This is the list of odoms that it has received from the odometer. Okay. I will explain what they mean shortly. So this is the real demonstration on a robot. I will now move to presentation and checking with the source code. Okay. In order to make that happen, we saw that there are many actions in play. So we will try to see what each one was. So there were 3 there were 3 main items to this. First one is a driver. That is the main program driver. Sorry. Oh, sorry. Sorry, I made that. Okay. I'm losing my phone. Maybe something. So
Are you trying to animate or?
I'm trying to annotate. Let me know if you can still see well. I'll try to work with this. Currently you have, if you can see my screen well, there is a driver. Okay, so the driver is the main program. Okay. There is a wall finder. So the main goal of this is to actually find the wall after having rotated towards it. Let's talk a little bit more about that. And then there is an action server. So this guy is actually keeping track of all the distance related parameters that are actually coming back from the odometer. Okay, so there are three different parts.
Okay.
In this, let's go into detail of one of them. So how did this actually come to be? So what is it exactly doing?
So
The
I'm assuming a
driver is
driver.
actually trying to
I'm assuming the driver is a node on its own. Is that right?
it's a node, yes. This is a
Yes.
node. An executable program can have multiple nodes in ROS.
All right.
A node is anything that can publish and subscribe to events in ROS
All right.
as a simplest form of explanation. And this node here, you can assume that it is actually trying to it is creating a publisher where it is actually publishing the velocity. Okay, when it actually starts.
Okay.
And it actually created a subscription to the LiDAR scanning because it needs the LiDAR parameters
Okay.
of the laser scans. And it actually has created a client, which is a client actually it will send an async request to kickstart it. It created an action client to interact with the action server. So these are the very high level blocks. And as you can see, when there were two parts of that demonstration we have seen. First is the part where you actually align with the wall, which is actually being done at the find underscore wall. The alignment with the wall requires that we actually receive the laser scan data, because we need to, when we are rotating, we are actually trying to scan to find what is the minimum ray distance of the index of the 0th index, to be a little bit loose definition. So 0 is in front. The sorry, 0 is towards the right, 180 is towards the left, and in the middle is actually the in front. And that definition actually is 0 to 360 and 0 to 720.
All right.
On the main real robot, I have seen 0 to 720, and on the simulator, I have seen 0 to 360.
Okay.
So in the middle, I have taken 20 each to actually gauge the distance. The general project says that take the middle, the center ray, and consider that as the minimum ray distance. Just to be a little bit more, I was trying to be a little bit more accurate, and I took 20 rays that in the middle, and try to calculate what is the minimum. I'll try to show you how that works. And so these are the main three parts that are there. As you can see, we are using one of the concept in the course is the multi-threaded executor, which means that we need to simultaneously receive multiple callback information, or while the callback information is coming, I would like to do some operations like publishing, where they should not interrupt each other by scheduling operations. So what we do is we create a multi-threaded executor so that the scan calls actually come through, and at the same time I don't miss the call that is actually coming to start the finding the wall operation. At the same time, I also need to continuously publish to command velocity. Okay, so this is a multi-threaded executor that I created for this type of callbacks. I'll show you in the source code what it looks like. They're mutually exclusive callback type. And the same thing exhibits to everything that is doing parallel processing, which is basically the scan subscriber as well, the driver of the program. Okay.
Did you say mutually exclusive callbacks there? You're saying you're using mutually exclusive callbacks?
This is mutually exclusive. Yes, I was. This is a multi-threaded executor. There's a spin, and these are mutually exclusive.
All right, I see.
Okay. I would like to quickly go back to the source code, if that's okay.
All right, let's go.
Show the source code. I'll try to first schedule this. Okay. Okay, sorry. Okay, so inside the source code, let's see through the source code. So this is the main driver file that I actually mentioned about. I will try to make that bigger. I'm sure it is visible.
Or you can make it full screen, then yeah.
No, I can zoom in. It's okay. It should be easier. Is it any better? Okay. So in this, we start with let's go with the main function. There you go. The main function actually created is trying to talk to the find wall service. Okay. And we are trying to create the find wall request. Then we send an asynchronous request for it. Then we wait for the request to complete. In the meanwhile, I created a node client and a node and added, please don't mind the names, just a programming part. The node client, so the node client is actually a my action client, and the node is actually a scan subscriber. The scan subscriber is actually a class that has a callback group, um, uh, for mutually exclusive callback group. It has subscription options, and it has subscribed to the laser scan data. The laser scan data is reading from the topic/scan, is being sent to the scan underscore callback. Once we have received the scan underscore callback, uh, we consider the range of the laser data that is actually coming in. I'll show you that laser structure, and we go either ways. So from the middle, we actually go either ways, by either ways 20, which is basically just take 20 scans to the left and 20 scans to the right from the middle, just to make sure that I get the minimum of those. And same thing with the right and the left, so that and after I get the front distance, the left distance, and the right distance, okay, which is the maximum of those rays, then I take an action based on the sensitivity parameters that are actually there, which is basically if I actually find that I find myself too close to the wall, then I create a velocity and a turn angle, and I publish that command. This publishing of the command goes to the command velocity, command underscore velocity, um, topic, and the message is a twist. Let me quickly show you what these messages look like. Uh, these messages actually contain this data that actually comes from these sensor related messages. This is a standard structure. So every time you receive a callback message, this is the full details that it actually gives. And we are interested in the ranges. For example, in laser scan, wherein it takes one full laser scan and gives all the distances inside a range of arrays in float 32. Okay? And the twist array contains two parameters. One is the linear and the angular velocity related parameters. If we go inside, we will find ourselves with a I lost the word for it, quadruple, X, Y, Z, to start with. And then we will know that we can set the linear and the angular velocity parameters. And we also, this is the odometry message that is actually coming. We needed this because we actually are trying to receive the odometry information, which is a position information, and then translate that into a distance. We have a distance, we have the distance. We are also trying to make sure that we take the X, Y, and theta positions from the position with covariance. That's why we need this odometry message. Okay.
Okay. Can you please explain more why you have to take them with covariance there?
Let me quickly show you what I did so that I can. Here you go. This is the callback I will receive for the odometric callback. And inside this, I did two things. One is I took the pose and the position. I took the X and the Y position, X and the Y position from here. Then I kept track of the original X and Y there where I started this, and I calculated the delta with a simple distance formula between Cartesian coordinates. And I took the distance and I kept adding it until I find something in the range. The range I fine-tuned, we can keep this as any delta. This range, at that point, I actually count. I keep a small threshold that says that I should avoid the initial starting point. So I actually did the greater than 3 so that I know one lap has for sure finished. So regarding your question, I took the pose with the parameters. Actually, I didn't take the pose with the covariance. I actually took the pose and realized it is actually the covariance, pose with the covariance. I later realized when I was doing the URDF course that pose with covariance comes with independent XY calculation, or at least that's the way I understood, wherein you don't have a reference 000 coordinates.
So you're saying you don't have a reference of 00 coordinates. Can you say that last statement?
Yeah, I didn't. When I started this didn't come with a 000. I mean, when I start this, it doesn't start at 000.
Okay, so you were trying to compensate for that, more or less.
No, I was not trying to compensate for that. I took the pose from the covariance from the X and Y from the pose because I was looking for X and Y to actually calculate the distance. I took it from the pose value. Are you
Oh,
saying I should have taken it from the
no, no, no,
from the?
no, it's
I'm sorry,
fine.
I did think that I didn't think that deeply. I found X and Y there. I it worked well for me as a position X and Y.
All right. Yeah, let's proceed. Don't worry about that.
Okay. Um, then I took as I said, I took one lap. I think that is one of the. I took the distance and I calculated one lap, and it came up to be yeah, greater than 3. 3 is an arbitrary value. Maybe with some advanced sensors, there is a different way to do that, where I don't need to keep track of the um, initial position, okay? Or in different environment, maybe it's not required. Let me show you a little bit about. So this is Action Server. So then and the lab uh,
All right. You've got 10
and the
minutes left
odometry
now.
calculation. This last bit about this find wall. Just one second. In the find wall, I think I did 3 steps. One is we find the shortest ray, okay, and then we rotate the robot towards the shortest ray, okay, and once we have centered the minimum ray, we actually assume that we actually hit the wall, and then we turn around so that we are going towards the wall, around the wall, okay. Those are the 3 steps it's doing. Once it has finished that, it actually does the response wall found as true and sends a message that is looks like this.
All right. So
Action mess.
you're saying it will start moving only after that one is found. After it is been set to true.
Yeah,
All right.
well, it has to first, it has to first align with the wall and then start the movement
All right.
around the, yeah. And here is the message. It's here. This is the action message format. It is having a list of atoms that we saw earlier and the current total distance, and find wall message that actually you, if I remember correctly, has nothing, just one. Yep, it says wall found is true.
All right. All right. Is that all?
Yeah, yeah.
All right.
That's all I had for this.
So thank you very much for your presentation. I'm
Yeah.
just gonna ask you a few questions about what you've been talking about. So you spoke about the use of mutually exclusive executor. Can you just get into more details about why you chose to use mutually exclusive ones? Did you have things that were conflicting or that were happening at the same time or that were blocking each other?
Yes, I saw that the blocking actually happens when 2 callbacks are coming with each other. Like you have 2 registrations.
Okay.
Until one of them is actually finished, the other one is on hold.
Okay.
So I created a mutually exclusive callback group, and both of them get executed at the finest granularity I needed.
Okay. All right. That's good. That's good. So can you also go into your script that implements the service that keeps track of the odometry?
Keeps track of odometry.
So I remember you used the
Odometry.
minimum value of 3. So you're saying your robot
Yeah.
will only start checking that it has arrived there. It has completed the loop after the 3 meter mark. Is that right?
Correct, yes. I noticed that when it takes, it's greater than 4,
Mm-hmm.
and I made that it was a convenient aftermath rather than a thought.
Okay. All right.
The reason why this was required, that if I didn't do that, it would just not start. It computes a lap at the same distance.
Okay. All right. It won't. Okay. So you had to make it slightly smaller than the actual size of the.
Yeah. Actual lap distance of the entire rotation area around this.
Okay. That's quite good. Let me see if I have any other questions. You spoke about something happening asynchronously. Let me see what it was. Oh, that was the ones that.
Async request towards the find wall.
Yes. Can you talk about a little bit more why you have to have it happening asynchronously with relation to this application?
I wanted it to wait until one is that I wanted it to let me show you that piece of the source code. I believe you. So first, I this is the place. First, what I did is I created a client towards the find wall service. Then I composed a message asking you to find a wall and do the full request. Then I created a future where I'm waiting for the response to be completed, and I waited until it was complete. So there is, to be honest with you, I really found I spent a lot of time trying to find a synchronous version of this, but I didn't realize that it didn't exist, and this is probably this is the best shot we have because we can then execute something else in other cases
Okay.
before the promise is got.
So are you saying this is always running when your robot is following the wall? Is it always checking? Am I next to the wall using this asynchronous find wall?
No, no. After the find wall is complete, the request is completed for the find wall service.
Mm-hmm.
Once you find the wall and align yourself, what this main service is actually doing is it is trying to keep itself aligned towards the wall by moving a little bit to the left side and a little bit back, and rotating when it finds an obstruction.
Okay. Okay. All right. I think that is it from my side. So again, thank you very much for your wonderful
No.
presentation. Um,
Okay.
I'm gonna we're gonna
I think we should. Can we continue? Yeah, I have another one to show.
Okay, you wanna get into that one? Let me just
Yeah, sure.
let's just
I
finish
need to
this one
switch.
and then you can go on to the
Oh,
next
sure.
one.
Okay.
Yeah.
Yeah.
All right. So I'm gonna stop your screen share now.
Okay. I can stop it. I did.
Alright, so that is it from us, people. So you can be one of these people who can come and present their development on a real robot and watch how their code performs on real robots, and you will be able to get a certificate from us depending on how you do. We highly encourage that you take your time to consider doing this, and until next time, thank you.